Hey, welcome back. This is a tale of surprises with used machines. What you see next to me, this is the main casting of the indexing head of my Deckel FP1 milling machine. That's also, but as you can see, there is nothing in it. It's completely emptied out because there was a little problem. And I guess the lesson with used machines is you can always expect a surprise. So when I bought the machine, I knew that the machine is in good condition. It was checked, but the accessories are basically, they took one in good condition off the shelf and supplied it with the machine. Having the indexing head inspected and then put into the package that I purchased would have added extra money. So kind of took the gamble and just did an uninspected purchase. I mean, they looked at it and from the outside it's in perfectly good condition. And it never gave me real trouble, and it kind of still doesn't. It worked perfectly fine, but I noticed when I used a worm drive to spin the spindle of the indexing head, which you do a lot, that there is one spot that feels a little bit funky on the 360 degrees of rotation. Due to another happenstance, I was planning to take it apart anyways because I'm looking into getting a rotary encoder mounted into this thing some way or the other. Not sure if I'm going to do it because it will be awful expensive, but it would add some convenience. So I took the indexing head apart and I have some footage of me pulling the spindle with a long threaded rod out of the casting. The worm gear on the back is semi-pressed on, and there is some other stuff, some spacers also pressed on. So you have to pull the spindle out to the front with a threaded rod, or you hammer the backside of the spindle through, but we don't do that. What I noticed when I inspected all the parts is this indexing head was rebuilt at some point in time, because the main bearing up on top, I will show you that later, the main bearing on top has been machined away and recast with Muglis Way epoxy. And when I talked to Arnold Werkzeugmaschinen, the people who I bought this from, who also rebuild machines, they for example did my Weiler lathe, they mentioned that they don't do that. There are companies who use the epoxy for rebuilding the taper bearing on these indexing heads. They scrape the taper. And what I also noticed is that the worm gear here had two issues. First of all, some special kind of person hand cranked it about 1,000,000 times with the worm half engaged, and that creates a very, very funky wear pattern. That you see that unfortunately very often. Having the worm half engaged and then cranking, and you create a terrible wear pattern. And also there is a high chance of breaking the teeth because you are moving the contact point farther away from the pitch diameter of the gear. It means you have more leverage, and well, one gear is broken off, most of it, and it happens to be in a way so you almost don't notice it, and it to my knowledge it didn't affect the accuracy very much. Well, I couldn't notice it, so that's a very funky mode of failure. I will show you that in a second close up, but just give you all the backstory right ahead. So asked Arnold, hey, do you happen to have a donor indexing head that I could take apart, or do you happen to have a worm gear that you can send me? And well, was my lucky day. There is it's in very good condition. It has some scars from somebody using it with the worm engaged like 5%. So there is a little bit of a groove scarred into the circumference of the worm gear, but nothing really problematic. The mating surfaces of the worm itself look like they are freshly machined, so that's a winner. So thank you, Arnold. Oh no, Jacksock machine. I really like to work with these people. This video is not sponsored. I left a lot of money at the company with this machine and with the other machine, and service from them and social interaction with them has always been very, very good. So can highly recommend them. So got the gear, and now this thing needs to go back together. What I do not know, and I've got to ask, to be frank, if I have to re-shim this gear to get the contact pattern between the gear and the worm perfectly in line. But we will see. We'll glue up the gear and the worm and just check it ourselves. So here's a close-up of the worm gear. And as you can see, there is this groove on its circumference. And this comes from either the worm being way too far engaged and really forced to spin the gear, or what I think what's happened in this case, since the damaged area is so far off center, somebody used it with the worm very, very partial disengaged. So when you disengage it, the worm sits on a eccentric bushing, and then it goes off center and slowly disengages. And somebody had it disengaged very, very far and still used it. Either they spun the indexer by hand against a little bit of engagement on the worm and they chewed away on the gear like that. There is also damage on the flanks of the gear. So I think they had it partially disengaged, and then they really went on and used it forever and ever and ever and hand cranked it, and this created this funny wear pattern down here, and this is really unnecessary. Oh, and here is the broken tooth. As you can see, this is an old crack. This is not bright shiny metal. I'm not entirely sure what happened, but I think with the partial engaged worm, the contact patch moves farther up on the teeth, and that gives a way higher leverage against the tooth, and that just snapped it off. And for wear properties, Deckel obviously decided that cast iron is the correct material for this gear, and there are pros and cons to this. This puts the wear on the gear compared to the worm. One could argue that you want to even out the wear between those two. One could argue that a hard bronze would be a better material for this gear. I'm not an expert. I'm just playing one here on the internet. So yeah, you could also argue that this needs to be hardened and ground. I wouldn't be too mad if that was the case, but it's not. So I have to deal with what happened, what's going on here. Luckily, I was able to source a replacement gear from Arnold. Otherwise, I have talked with Alex from their channel, An Engineer's Finding. Alex was here recently. It was a really cool visit. We talk shopped for 10 hours. And if I couldn't get a replacement gear, I would have done what he did, and I would have fly cut a new worm gear. I would have created the exact shape cutter as a fly cutter and used the Moore rotary table that I have that indexes very precisely to cut the gear profile into a blank. But fortunately, I don't have to do that. Unfortunately for you, because that would make for a great video. But if you want to see gear cutting that way, head over to Alex's channel. And since he didn't have a high precision rotary table, he used a fiolidite for indexing. So that was a really cool project. So head over there and have a look at that. The construction of this is in one way very simple, but on the other way very rugged. So it's great. Very happy that the rest of it is in great condition. The worm itself has no damage whatsoever. It has some discoloration from old age. I will polish it up in the lathe. Same for the... Oh, that's the main spindle. That's a 40 taper spindle, and it runs just in a plain bore here and here, and it has a tapered surface up here that rests in a mating taper. So that's a very, very stiff arrangement. So this is the front tapered bearing of the indexing head. This in here is a cylindrical bore. This is a straight bore in the casting. What we see here, this black surface here that I'm scratching with my wooden poker, not really scratching, that's just the grease on here. This black layer is Muglis bearing epoxy, or a similar bearing epoxy. It's probably Muglis from Diamant or one of the SK bearing epoxies. And they did this really quite nicely. I was always curious why this indexing head has this separate hole here. This is not original. I was always a little bit curious when you used the grease nipple back here to lubricate it, and this is usually plugged with a set screw. If you take it out, grease gets squeezed out here. So I wasn't really sure. It was like, I thought it's kind of a modification to show that it's greased properly. But what this really is, now that I see that it has been cast with the epoxy, they use this to inject the epoxy, and there is a little cutout over here, a little slot where you can see that the epoxy goes all the way to the outside. This is the overflow, the riser to say in casting speak. What they did is they took the spindle, they placed it in here, and you see these little dots. They are 3, and they're roughly 120 degrees apart. I think they had some spacers in here. They either glued in or I'm not sure. They had something in here. They had the spacers in here. They put the spindle in, and then they injected the Muglis from here, the epoxy. So it filled all the way around the spindle taper until it came out on this side through this riser slot. Everything, of course, with mold release wax. And then after hardening, they pressed the spindle out and they cut off, they machined the Muglis nicely flush here, and they cut the Muglis in here. They chamfered everything. This is really done very well. This is how it should be done. And I'm not going to muck around with this. This is perfectly fine. So yeah, that's the Muglis tapered bearing. The main bearing. Let's go to the other side of the indexing head. So now you're looking in from the back side. Out here would be the large graduated dial. And what you see is one straight through bore. Also, my script for this video mentions that I shouldn't make a joke at this point. I don't make jokes. You can see a long groove in here going the full length of the slot, and it's terminating down here on this face, and it's also terminating into the taper. And these indexing heads are meant to be greased. You put standard lithium grease in them, and the grease will walk its way all the way along this main bore, lubricate this end surface and also the tapered bearing. There is a second grease fitting for the warm drive. So this is again overview. For those not familiar with these Euro milling machines, this shape might be a little bit unfamiliar looking or unconventional looking. That's because they are meant to be held vertically against the apron of the milling machine. So the spindle is most of the time vertical. You are not using these on a machine table like this usually. You can, in some cases, setups require this, but most of the time it's not done. So warm drive would be here with the indexing disc or the graduated dial or both. The way this one is set up, it can hold both. Here is the overarm support for the tailstock. This slides in the dovetail. Here would be the clamp for the spindle. I would have shown it in a complete before I took it apart, but well, I didn't I didn't plan to make a video on tearing this down. But now that I have it apart and a damaged part, well, going to show it to you. People seem to like tear down videos and reassembly videos for for some closure on a story. But we will put this back together in this video. I'm not going to do a multiple part series on this thing. This is the main spindle of the indexing head. I have it clamped on the inside, the 6 jaw back here, and supported with a pipe center on the 40 taper end. And I'm just quickly polishing up these 2 sections here and the taper surface because they have a little bit of discoloration. Somebody used this indexer at some point in time with water-based coolant, and water-based coolant wreaks havoc on every machine tool. If you go to any machine tool rebuilder and you walk into their disassembly area and you look at the machines, at the parts, at the mating surfaces, plain bearings, sliding surfaces, accessories that get mounted, clamping surface, everything that cannot be easily dried off by the operator of the machine will rust. It's an utter nightmare. There are certain water-based coolants that have such high of a oil content that they do not promote rust, but your average water-based coolant is on this type of machine, on manual machines, it's really not good for the machine. That's why I'm running straight cutting oil in my 2 machines. Well, 3 machines and a CNC mill too. And what I'm using for polishing is 1 micron grit lapping film. This is very, very, very fine aluminum oxide, basically emery paper, but on a polymer carrier sheet. This happens to be self-adhesive even. You can pull the backer off and then it's sticky, so you can make your own sanding sticks or lapping plates with the stuff. I think it's from 3M. I got a well, a friend of mine buys or has to use full sheets, and for some reason the application requires to cut it down a little bit, and I got a pile of the cutoffs, so I'm I'm good with lapping film in the 1 micron range. So just polishing these journals up a little bit, not altering the surface the geometry, just cleaning them up. In this area we see some severe discoloration. This is rust pitting. This is the area where the spindle is clamped from the outside with a split cotter. A split cotter looks like this. It sits against the spindle in a cross bore that's not going through the center line. It's tangential to the spindle. And these 2 cotters get pulled together and clamp the spindle in the bore. And coolant and water came through the bore of this clamp and started to eat away on the spindle. So there is some pitting on here, but there is enough surface, good surface topography left, so I'm not worried about that. I'm just polishing it up so there is nothing sticking up. I think we could hit it with some precision ground stones. So yeah, the stones, just by feeling the surface, tell me that there is nothing sticking up. So just following with the 1 micron lapping film to clean it up. I'm running the lathe at 330 RPM. I don't want this to spin this up to 3000 RPM. I dwelled a little bit longer in the area of the rust pitting, but this is not going to alter anything. And I don't think that this pitting is affecting the performance of the indexing head. I didn't notice it until now, and I won't notice it in future, I guess. I'm also going to hit the taper bearing here. I already hit it before filming it. It had some discoloration on it from oil and maybe coolant. So taking the lapping film, and I stuck it to the end of this bamboo skewer. No need to overdo it. And I stuck it to the skewer because I don't want to get my finger in here polishing and get possibly cut or caught by this edge if I jam my fingers in here and get one hell of a spin here. There shouldn't be any free abrasives from the lapping film or the precision bench stones, but I'm still going to clean it very thoroughly, blowing it off, washing it off with isopropyl alcohol, just to make sure I don't get any stray abrasive particles back on assembly. There's an O-ring groove on the inside of this flange. There is the O-ring groove in there. An O-ring goes in there, and this seals the spindle, the front bearing portion, against the casting. And this seems to work very well against chips and fine dust. When I took this apart, the grease in there was clean, and there were no particles in the grease. So I guess this works very well. It's not only a seal, but it also wraps around and creates a labyrinth. That's quite good design. This indexing head was meant to be used. It was designed to hold up to proper use. It's not like a thing that you use from time to time. This was meant as a main work holding implement or a main replacement for the table. So yeah, that's the taper surface. It looks really, really good. Surface finishes. This indexing head is probably, well, we have 2025. This is older than 50 years, I guess. And apart from this pitting here, hard to see on camera, I guess. Apart from this pitting here, that's the only damage I can find on the spindle, and this will not be a problem. I decided to take it completely apart, every single screw, while I'm at it. And also I took the majority of the parts and I drew them up in CAD so I can use the 3D model later if I decide to add an encoder ring to the back of it. So here are all the internal parts. And over here are the casting of the right angle bracket that holds the indexing head to the apron of the mill. Already cleaned them. Everything is looking very good. A bunch of hardware that needs to be cleaned. A 5-liter canister, or 1 gallon, I guess. Most cut down halfway makes a great cleaning tub. Very chemical resistant, of course. And over here, there's the main casting of the indexer. This needs some cleaning still, but we're doing well. The O-rings for the sealing of the spindle are arrived. And over here on the milling machine, well, when I did the teardown and cleanup of this large rotary table, I mentioned that I'm probably never going to use it, and well, turns out it's a nice fallback option if the if the indexing head is down. So mounted the rigid table and the rotary table, and that got me along this week. So yeah, good thing to have it. And I have to say, the large rotary table is quite nice. It's the combination of a rigid table and this large rotary table is very, very stiff. It's significant more stiff than the indexing head, but the indexing head is a little bit more nimble, and also it's not like 55 kilograms, not 80 kilograms hanging off the apron of the mill. The indexer is, not gonna lie, I think it's about 45 to 50 kilograms, so significant lighter than this combo. So these parts need to be cleaned. And what I found works best for oil and grease is just a solvent or an oil-like substance like WD-40 or similar. In my case, it's straight petroleum. And I just use a very stiff brush, and I clean the parts like this. Yeah, a washing table would be nice, but I don't have room for... I used to have a small benchtop wash table that I built myself, but I didn't use it enough, and also I cannot justify the space use of it, and also something like a floor-standing BioCircle cleaner would be nice, but in all honesty, I'm a machine shop, not a repair shop. I'm a prototype shop, not a repair shop. That's what I wanted to say. If I have to clean once or twice something really, really dirty like these parts here, this works perfectly fine. This is a super simple solution. It's minimal amount of solvent that I need to get rid of afterwards. The person who assembled this indexer last used molybdenum disulfide grease on all the threads of this right angle attachment, which is a good choice, of course, but it's well, it's very dirty when you take it apart. You look like the Tin Man from Wizard of Oz if you are not careful. I tried to clean up those washers on the sanding plate, and as you can see, it's cleaned up a ring around this central area. And that's where years and years of tightening those nuts just mushed down the material. And on, let's see, I had one that was particularly bad. This one, I didn't even bother to clean up the front here. On the back side, I hit the back side on the sanding plate, and the sandpaper cleaned up here, and only the small ring surface here. So this washer, let's find a straight edge. As you can see, out here on the right side, it's barely making contact in here on the bore, but it doesn't make contact at all out here. It's probably not going to harm anything in regards of stiffness, because once you tighten down an M12 screw, it will squeeze everything into submission. But it will damage the bores, the spot face surface of the bore over time. And I don't want that. So I'm going ahead, since I need to order tooling anyways, I'm going to order some hardened fixture washers. These bores are for the clamps that hold the overarm support in place. So already used a brush to loosen up all baked in crud. Now I'm going to use some compressed air and a rag. to clean the bores out completely. When you do something like that, be sure that you close off all openings with the rag, otherwise you get a very directed stream of nastiness. Trying to get this rusted pin out here. That has definitely seen a lot of coolant. And this is the stop pin for the eccentric worm engagement. And I see a problem coming up to me. This is just a cheap vice grip welded to a slide hammer. But I feel... Oh yeah. This means trouble. I hope I don't have to machine it out. I think first I'm going to try to weld a little bit of just add a little bit of weld that hangs over the edge of the pin so I can get a more positive grip on this tiny pin. If that doesn't work, I can still weld something like the nut to it and screw, or I can weld a set screw to it and grab it with the slide hammer that way. But I would like to replace this pin, because since it defines the rotational stop of the worm engagement, it would be nice if this was not a rusted and pitted surface. So I think I'm going to try welding first. I'm going to use some Chronitex 252C filler rod. With this stuff, you can weld something like an Inconel turbine plate to a piece of birch plywood and it will hold up. Let's see if this gives me enough purchase with the slide hammer to pull on this pin. The heat might also help to free it up. I would prefer not to have to machine it out there. Oh. This is not promising. Nope. Let's try welding this M8 set screw, hardened set screw. The slide hammer I'm using is just a piece of M8 all thread, 2 flange nuts Loctited on, and a M8 coupler nut on the end here. So I can use anything that has an M8 thread. I just fuse welded it, didn't add any additional filler. There's plenty of the high nickel filler rod on this pin anyway. There we go. Doink. Oh, that was easier than I expected. Well, it was harder than I expected and it was easier at the same time. As usual, each project is one broken bolt away from becoming a nightmare. So I have to find a new 5mm dowel pin. I think I have one. And this is one for the scrap bin. Despite me doing a lot of very small work, I'm not afraid of using a sledgehammer and a welder. I decided to drill this hole for the stop pin through, so next time I have to change the pin, or the guy working on this after me has an easier time. So it's a little bit harder than it looks, because you have to align the part with the pin, and at the same time align it in the vise so it gets clamped centered up. This would be easier with a normal vise or just clamping it down on a V-block, but I'm too lazy to pull the vise off here. But yeah, this looks good. Doesn't interfere. I'm just going to use, really, I wanted to, I have the vise flipped 180 degrees, so this side here opens the jaws in the tighten direction, in the normal anticipated tighten direction. So tighten, pull this off, don't muck around with it. And I'm just going to drill through with a 2mm drill, so you can use a small pin punch from the other side. Let's see if this thing is, I haven't checked if it's hard, but I think this is a casting. Yeah, that definitely was cast iron. And now, the next guy that has to work on this will thank me. Hopefully it's not me. Now this is a through hole and I can use a pin punch to get this pin out again if there is a problem. Don't hesitate to make small improvements like this if it doesn't do any harm. Assembling it with a little bit of oil and a copper drift. Bottom it out and checking if we are. That's perfect. Okay, first we have to assemble the worm drive. Well, the worm bearing, I guess. This is the eccentric housing that allows you to engage and disengage the worm, and also to set the clearance between the worm gear and the worm. So the way they designed this is it gets assembled from this side, if I remember correctly. Ooh. Yeah, this is a very tight fit, by the way. But I don't want to assemble it dry. I think we're going to assemble it with grease, because that's what I'm going to lubricate it later too. So when dealing with grease in one of those 400-gram capsules, always use something clean to grab a little bit of grease out of there, and never go with dirty tool in there. I think I don't have to explain you why dirt in the grease would be a problem. But still, if you look through the manuals from SKF, one of the main reasons why bearings fail is dirt in the grease and assembly mistakes or damaging the bearings through assembly. So getting a little bit onto this face bearing here. Since all of this will be grease lubricated later anyways, I don't have to be, I can go very greasy here. Now we need the end bearing. And there's a bronze bearing on this end that can be adjusted in and out. With this cap nut that goes into the end here. This has a small register pin so it doesn't spin with the shaft. In like so. There we go. Let's try. Always check for clearance here. So it don't bind anything up. This looks good. This feels also good. These cap nuts are slit. They take a single countersunk screw for locking them. I'm just going to use a little bit of the grease on the threads. Really want to make disassembly next time super easy. My collection of adjustable, oh, this one fits. My collection of adjustable face pin spanners is embarrassing. But turns out I have one for this particular border ender. Let's see, we have the clever thing to do when you take something apart is to not sort by assembly, but just throw anything in one box so you get this nice game of find the right screw. I think the right order of assembly is to put the worm drive in first, then you push the spindle through, or then you put the worm gear in and then you push the spindle through the worm gear. You have to do kind of two things at the same time there. Just checking. Okay, that goes. Well, could be. Yeah, you definitely have to get the worm drive in first because well, I'm going to show it to you. The worm needs to go in first because when you put it into the bore, you have this leading part of this housing sticking into this large clearance bore, and that's where the worm will sit. So if the worm gear is already in there, you can't assemble it anymore. You can't put the worm in from the side. This needs to go in here. Then you spin it out fully out of engagement like this. And then you can get I think it goes in this way, the gear in here, and then the worm can engage the gear. These handles are quite nifty. They are very similar to the modern kip style handle that are adjustable. You can pull these and you can adjust them so your handle orientation and clamped condition is always as you want it. And these are different style. They go together like this. First spring, then you have this part, the handle with the spline drive. This goes over the hub. Then you have a retainer screw. And for adjusting these, you need to push in. Then you can adjust them. Quite nifty. So the hub goes on here. These are usually easier to assemble when you don't have the handle on because you can just free spin it. And we add the spring, the handle, and then the retainer screw. And now we can happily adjust it like we need it. So it's in a convenient position when we clamp it. There is a threaded countersunk hole back here, and that's for a screw. I think it's this screw because somebody already machined the underside of the head to go in deeper. This is the stop screw where the pin that we extracted from the worm bearing assembly, the pin hits against this screw for a constant engagement with the worm. We will adjust that later. Hey, why didn't you say anything? I just noticed that I assembled the worm housing in the casting completely dry. One could argue that all these parts will get the next part will be really tricky getting the spindle in. Well, spindle is easy. The other thing is the hard thing. Oh, and we cannot forget to mount the lock. If we forget the lock, we can start all over again. The lock is the split cotter style. You have these two parts that are separated with a spring, and they go into this bore. And when you tighten the nut on this end, they pinch together, and they pinch against the spindle and in the bore. It's a very simple and very effective lock. In theory, it's pushing the spindle out of position, but it's fine in this case. This is all, there's a huge amount of bearing surface, so it's not critical. Also, this is not like a jig bore indexing head. This is a milling machine. I'm going to drop this in. This is very greasy. As you can see, it's spring-loaded. A little bit of alignment. So push the spindle in, we don't get into trouble. The bore on the replacement gear at some point in time was a little bit damaged on one end. And I turned an aluminum mandrel about 20 micron undersize, just using some silicon carbide lapping compound, which cuts very freely, but doesn't embed. It doesn't charge into the cast iron, from my experience. Well, it will break down so far that it's not abrasive anymore. We'll try to do it by hand first. I can work it through. Something tells me I need to clean this off again. I don't want to work the entire bore. I want to work this end. So I'm going to put the lapping compound on this end of the bore instead. I think this is the better way than running a flapper wheel on an air die grinder through the part. There we go. I have either worn the mandrel down or the high spot in the bore of the gear. We'll see that in a second. I will run it on the power back and forth a few times, also flip it around and run it back and forth a few times, just to even out everything. But Stefan, this mandrel is not expanded. It's undersized. Yeah, it's undersized, but I'm adding the grit. The grit has a dimension to it too. And from my experience, if you just want to clean up a bore a little bit, you can just turn it a little bit undersized, add the lapping compound, and rely on the rolling abrasion of the grit. Yeah, this feels good. Let's flip it around. Yeah, that's way more civilized than running a flap wheel for sure. Also abrading, of course, the aluminum mandrel at the same time. So the material you can remove with this technique is very, very limited. I put it together with some felt marker on the teeth and cranked it 360 degrees all the way around. And what I get is a contact pattern with between the worm and the gear that is slightly offset towards this side. You can see this bright shiny spot down here, and to my logic, I have to look it up on the internet. I think I have to remove some material on this side so the worm sits here, makes contact further to the right, and when I remove material here, the gear goes more to the center line of the worm, I think. Could be wrong here, but that's what I'm going to do. I'm going to grind off like 20 micron to start from this side. I could also reduce the spacer disc, but the spacer disc is in very good condition. I'm not going to touch it. This face of the gear is not brilliantly. It has some. It has some history to it. Let's say it like that. I want this to move over very, very slightly, then it should be fine. I did one iteration off camera because you don't need to see the same over and over. In total, I ground off 30 microns off the face of the gear, just on a surface grinder, put it flat on a magnet, dust it off. Let's put some blue on here. I hope you all know this trick with Sharpie and compressed air to give you a miniature spray can. So put some oil on here, just the assembly is easier. The relapped bore is still a mighty tight fit. I can get it about to here with hand force. And then I would either have to hammer or pull it on with a threaded rod. But for testing the gear mesh, I can just pull the spindle in all the way so so the face of the gear rests against the shim disc and the housing. And then I can engage the worm like this. And I can spin it. Let's make a marker here. So I go both orientations 360 degrees. This is riveting content. And that's one full revolution in one orientation, but we want both flanks of the worm printing against the gear. So we go opposite direction. It cranks very nicely, despite running fairly dry. I don't have any oil or something on the worm itself. So there is a little bit of a limit of how often I want to do this. There we go. And to get the gear off the spindle, I figured I can use, well, I need to disengage the worm for this. I can use the spindle itself as a slide hammer. I can't damage anything. The gear rests against the shim and the shim rests against the housing, and the spindle is perfectly guided in this massive long precision bore. So no danger of damaging anything apart from my fingers if I get them in the wrong spot. This is a very civilized way of taking it apart. But I can look at the contact pattern, and it's really good. I like it. I'm going to leave it like that. This is really hard to film. Everything is playing against me here. You can see the entire tooth is blued up, but there is a a semicircular contact patch that follows the curvature of the root of this tooth gap. And that means that we're making pretty much very good contact along this, this tooth. And that way we get very good contact and also very even and very good wear properties. Same on this one here. This looks really good. I'm going to leave it like that. Yeah, this one too. This is one of the buggered up tooth. The tip of the tooth here had contact with a partially engaged worm. Also, if you look at this area here on the teeth, on some of the teeth, that's also from a partial engaged worm. Let's figure out if we can do this without hammering onto everything. I think I can do the entire stack-up assembly. See. This is just a plastic cover with a felt ring on the inside. This goes here. This runs against this outer diameter of the worm gear. And I almost forgot the O-ring. This is an 88mm ID and 2mm thickness O-ring. This goes into this groove. Oh yeah, this would have been mildly easier beforehand, but it is what it is. Getting this O-ring situated in this O-ring groove in there, you see about nothing in there, I guess. We'll see. Yeah, this flashlight is about useless. So, well, you see still nothing. Trust me, it's in there, it's sitting in the groove, and this register surface needs to be oiled up, otherwise this does not go together. Now the O-ring has squeegeed over the edge, and I can feel it fully engage. What's nice about, I ordered 2 different sizes of O-rings, and the seller threw those O-rings unmarked in the same envelope. Thank you very much. Why can't anything ever be easy? So that's the lock. So now that the O-ring is in there, we can do our stack up back here. And put this all back together. These are the 3 discs that make up the back plate. We have this locking collar on the inside that gets that clamps this graduated disc, which also is the direct indexing disc. We need to put this in too before we close our stack up here. There's a lot of things to consider, and I will run, these parts are still dirty, so cleaning those up. Please excuse me going a little bit on the fast side through this minor rebuild. I need this indexing head back operational. That's quite an important piece of equipment for me. And I have a metric ton of work lined up. I'm dancing around the parts of the disassembled indexing head for a week already now, and that much chaos in the shop really gets on my nerves. So I decided to take the evening, or the night in this case. It's quite late, to get as far as possible with the reassembly of this thing. So Next piece is the direct indexing plunger. This goes in here. Yep, that looks good. That's moving freely. And we have this little lever that screws in. On the side, there is a slot in the casting. Where this handle screws in. And this allows you to move and lock the indexing pin. Here you can see the bayonet slot. This is super awkward with the left hand around the camera. So, this should. Yeah, no, this is normal. Needs a few cycles to spread the lubricant and have the spring settled nicely. So this is in place. I think that's everything that we have to put in before we mount the direct indexing assembly. Direct indexing assembly is this free spinning hub that can be clamped with those 4 screws to the direct indexing disc itself. And this goes on like this. Now we just need to pull it all together. Yikes! That hurt. And also I pushed the O-ring out of. Oh no. Okay, this will cost me some nerves. Using a long threaded rod and 2 strap clamps, I think I should be able to I can already see the 500 reclamation to do this better in the comment. And I appreciate that. Maybe they will help somebody who has to do the same. But I will be done at that point. Something. Oh, okay. Yeah, I bottomed out with the. I have my safety sandals on today, so I have to be a little bit careful. So this is almost all the way on there. Do I have a piece of pipe? I have something that I can use. Here. There's another ideal because this has a relatively close fitting board. Larger diameter would be nice, but I don't have any piece of pipe or something that I could use. The problem is the gear that I'm using now as a push pull needs to be aligned very, very good. Otherwise, it will bind up immediately. There we go. Would be funny if I couldn't get the gear off now. Maybe we should. I think I can do the rest with the nut. So we can take this Mickey Mouse solution apart before I lose my mind. Yeah, that's enough thread now that I can use the nut to pull the rest together, and we can also the direct indexing was engaged. But yeah, nothing binds up. I was panicking for a second. Let's see if the spindle lock can withstand this. Oh, there we go. That's quite the strong assembly. I mean, everything that's on the shaft needs to be a very tight fit, otherwise precision will be very determined by randomism. Checking my clip if it still moves freely. We're getting somewhere. I have to check the end play now, otherwise I don't know how far to go. You know, the problem is once I over-tighten the adjustment nut, I have to pull this whole assembly back a little bit, which is not as much fun as you might think it is. Okay, that's 170 micron, 0.17 millimeters. That means that's the distance that the nut needs to travel to zero end play. Zero end play would be probably a problem. So let's see if we can. Let's do. Oh God. Okay. Oh, hey, I can just measure against the nut. This would be way easier. Okay, we have like 0.14 millimeters left. That's 0.06. It's to 0.1. Okay. Okay, this method works very, very nicely. I'm measuring the end plate by pushing it back and forth, and when I tighten the nut, I can measure how much the nut has moved from tightening, and that gives me a very accurate adjustment. You can see the dial test indicator here and my super dirty hands. And currently I'm at, just for you, I'm going to zero it out. And that's like close to 50 micron. I'm not going to adjust it to zero. I think that will create problems. You need some gap in a plain bearing. You can't adjust it to zero or you will properly bind it up. So I'm going to adjust it by maybe something like 30 microns now. So doing this around the camera is horrible because I can't see anything. You have to overcome all the interference fits on the shaft, and that's a lot of interference fits. Of course, I'm measuring some runout on the on the nut because the backside of this nut is not a precision surface. But I'm mostly interested in the end-to-end play. But this looks like 10 micron. And I'm going to leave it like that because I can still adjust it later if I feel like 10 micron is too much. But I think this is good. This was very exciting. So the adjustment nut has, of course, well, the adjustment nut has 2 set screws. These set screws, well, it has 1 set screw. These set screws have a brass pad that's pressing up against the thread, so you don't damage the thread. So I had to pull the indexing head apart again because I forgot a spacer ring on the inside and also 2 shims that adjust the end play, the in and out play of this eccentric bearing for the worm. So I had to pull out everything again, added those parts and put it back together. I did that off camera because it was followed by a lot of swearing. And what I also did is I took the screw here. Well, I took this screw here and I adjusted its length just by removing small amounts of material on the D-bit grinder on the end of the screw until I got for this worm and worm gear combination, correct engagement depth. Means as small as possible backlash while allowing to be cranked freely. So to show you the backlash, I engage the worm fully against the pin that we changed earlier, the one that I had to weld out and replace. This bumps up against the screw here that I just showed you, like this. And then you lock it. And then the worm is fully engaged. Means when I crank here, the indexer is spinning. When I have a pin on a magnet here, and I can take a dial test indicator to the top of this pin, top that center, and I zero it out. Then I just go back and forth on the spindle. This is the backlash I get. That's about 30 micron on a 90 millimeter diameter. That's not horrible. But that's 30 micron on a 44.5 millimeter radius. That correlates to a backlash of 0.03 divided by 44.5. That's the radius. And we take the sinus, and we get 0.03 degree. That's 2 arc minutes and 19 arc seconds. Is that good? Is that bad? I don't know. I know that I can work with this. Without a direct reading, without a digital encoder ring or a glass scale on the spindle that shows the actual position, you have to work with a approach direction of the indexing head anyways. You have to take the backlash always into account. Then it's not a big problem. So time to put this thing here back together. But this is non-critical. This is just the dial and the indexing discs. I have just the hand crank on here for easier spinning while playing around with it. The end play is set to something like 10 microns. It's very tight. So I'm very confident that this indexing head will be in great condition when I'm done here. I mean, it was in great condition apart from the star and worm gear that somebody completely buggered up. Just being a professional or a tradesman does not mean that you cannot be a that you do stuff like that. Assembly time. Let's put the dial ring and the indexing plates back together. This 1 minute, 1 arc minute reading dial is not standard on the indexing head, by the way. This goes on here. I want a little bit of lubrication on here, just so the anodize does not scratch on the steel directly, completely dry. That's not very nice. Also gives this draggy feeling of a precision instrument. If you ever dealt with a camera lens that moves really, really smooth, that's usually a very, very tenacious grease that creates this feeling. This is a leaf spring that goes in here. As you can see, it's not flat. And this bent segments, 3 of them, press down on this graduated dial to give it some preload and also keep it from sliding against the fixed part. So I'm going to put some grease on these contact points too. Again, just so things don't run dry. This ring gets mounted with 3 flathead screws slotted. I'm not interested in any comment about flathead screws. Usually, if done properly, they're perfectly fine. Yeah, I know torques exist. Here we have a little brass plug and a thumb screw. That's to lock the graduated dial in place. And then this goes on here like this. Let's see. This slides on here, so I would like some grease in here. And this goes on here. And we do this. Oh, these are ultra flathead. The ball end of this Allen key does not work with these. Well, it works, but you cannot exceed any torque on these screws using a straight end. Okay, and this goes on here like, oops, like this. Now there is 3 screws from the back side and a locking lever, which is a quite funny design choice. But I will show you how that goes together. So let's get this. I don't want to smash my fingers on this indexing head if it drops down. That would be rather unpleasant. So this bore here gets the clamping lever. That's this one. So when I tighten this, it locks the dial in place. You need this if you use the indexing plate. Normally this is open and you can use the entire dial ring. The other 3 screws, there are 4 more holes. are just screws with a spacer ring. And these get fully tightened, but due to the spacer ring, they hold the retainer plate on the inside in position, but still allow free movement. That was a little bit confusing when I took it apart. So the last part is the indexing disc. I usually keep this one on here. That's a quite useful range of holes. But as I said, I'm not using the indexing disc too much. I do most of my indexing either with the graduated dial or with the direct indexing on the backside. But it's still nice to have the option. This goes on here. There's a register pin that needs to line up. Maybe a little bit of grease on the bore. Make your... Don't be mean to yourself when you have to take stuff apart. Adding a little bit of grease does not hurt anybody. So this goes on here. And this holds the indexing disc in place. Next are the sector arms. These slide over here like this. And there is a small screw, slotted head, that locks the two pieces of the sector arms together. These don't need much torque at all. And then you have this funny spring that gets pushed in here like somehow. Like, ugh. One would think the industry would have came up with a better solution than this very painful to use spring, but they have not. So here is the sector arm adjustment, and you can move them around. Okay, that's that. And the last thing is the crank and pin combo, this thing. This is both the indexing pin. It can be locked out of position like this. And also a nice crank handle. The dial is not moving along. This is done with the indexing pin. This just sits in a random hole and drives the entire dial along. And when you want to do indexing, you lock the dial and indexing disc in place, then you can use your indexing pin as usual. Like this. But as I said, most of the time, this is open and I'm freewheeling, basically. And even more often, I have this completely disengaged, and you lock it when it's disengaged so it doesn't partially engage and create the trouble that I had to deal with. And then I can free spin it and use the direct indexing on the other side, which gives me 24 positions. I use that very much. Okay, it's back together. Woohoo! We're over at the surface plate, and I've put together a little bit of a setup to check the how well it indexes, for example, 90 or 180 degrees with the worm gear, with the new worm gear. Unfortunately, I have not checked this with the old one, but I never noticed any problems with the parts I made with it, which is funny because, as you have seen, one teeth of the gear is missing. So maybe it's not that critical. So I have a Moore 123 block, which is close to gauge quality, stuck to the face of the indexer with two magnets in a random orientation. And I use the worm drive of the indexer to align it horizontal with the surface plate, as good as I can with a 2 micron dial test indicator. I will show you the reading in a second. And now I can, for example, rotate it 180 degrees and check if I get the same reading. You might remember this indicator stand I made years ago. It's still in use. As you can see, this reads quite nicely side to side. As I said, this is a 2 micron indicator, and it shows less than 2 microns. So let's get it out of engagement. First, I want to play with the repeatability. I just crank it away from 0, and then I go back to 0. You won't see this as well as I do because of parallax error. But when doing precision work with dials, magnifier is not the worst idea. So there we go. That should be 0. This is more or less the repeatability of me reading the credited dial and my ability to line 2 lines up, and also if there is some funky business going on inside the index or something is loose or something like that. But don't expect that. So we start here and we're a little bit under 0. Yeah, it's well within 2 microns side to side. Keep in mind the surface plate isn't perfect either, so you're transferring a little bit of error from the surface plate too. Let's do 180 degrees. Since I don't have a 0 marker for the large rear dial in my view, I'm just making a small black spot here so I know how often to turn the hand crank. And of course I have to keep the approach direction in mind. I'm cranking always clockwise to get the backlash out of the equation. So we're close to 0. Now I'm looking at the dial down here. If somebody laughs at you for doing this, well, joke's on him. So since the block was not centered on the spindle, of course I have to get the dial test indicator in position again. I have the dial test indicator here in position. And that's looking pretty good. That's within 2 micron. So 0 here. If I did this with a 10 micron dial test indicator, I would barely see a reading. So yeah, that's like 2 micron and maybe a little bit of change for a 180 degree reversal of the part. Which is not bad, I would say. Let's quickly do the math. A 1, 2, 3 block is about, what's that? 75 millimeters. I need a calculator. So 75 mil, we had a reversal error of 0.002 millimeters divided by a distance of 75 millimeters. And we take the sinus of that and we put that into an angle. And that's an error of 5.5 arc seconds. That's quite neat. To properly qualify the indexing head, I could put it on, I could drag out the more rotary table that I have, which is 6 arc second guaranteed, and it's better from the test report. As far as I know, these indexing heads did not come with a polar chart mapping out the error across the 360 degree range. This is a milling machine indexing head. They guarantee their plus minus 45 arc seconds, and it's good for that purpose. The Moore indexing head, or Moore rotary table, is a jig borer and jig grinder tool, also a metrology tool. So that's one solid order of magnitude more accurate than this thing. On the other hand, this thing is built like a tank. You have seen the huge cylindrical bearing inside the casting, which goes full length without interruption, and the large conical bearing in front here. It's not prone against ham-fisted machinists that rotated with the worm partially engaged, but it is what it is. So yeah, that's 5.5 arc seconds reversal error, and that I'm very happy with that. I could repeat this a few times now with the magnet in different, with the 1 to 3 block in different orientations to see if there is some funny business going on. But I think, judging by how the worm gear that I put in there looked, it will be fine. Wouldn't be me if we didn't look at some old paperwork. I have the original sales brochure for the Deckel FP1 here. I think that's around 1970 dated. That's basically my machine. This is the configuration that I have with the round dials for speeds and feeds. The older versions have 2 levers each for speeds and feeds, and even older machines have change gears for setting the speeds. What I don't have is this huge funnel-shaped coolant tray that you can stick on top of the machine base. These tend to be in the way all the time. You bump your knee on this edge all the time, and most people don't bother with them. But what I want to show you is, since we are dealing with the indexing head, so here are the specs for the indexing head, Teilkopf. 40 taper spindle, takes collets up to 25 millimeters. That's with 40 taper collets. Standard accuracy of the indexing head is plus minus 90 arc seconds, but you could get a higher precision version, plus minus 45 arc seconds, so double the accuracy. But I do not know if you can tell from the outside if such a dividing head has one or the other. A gear and worm set put in them can be swung 90 degrees to either side and can be tilted 15 degrees against the machine or 6 degrees away from the machine. And the 40 taper version weighs 55 kilograms. So it's quite a chunky thing. To compare, let's see if we have the rigid table that I have mounted currently is 42 kilograms on its own. And then when you add the large rotary table on top, you come out at almost 80 kilograms in total. So in my case, the indexing head put less strain on the C-axis ways and lead screw. So there's the machine again. And what I wanted to show you, well, there's a lot of pretty pictures, but there are really a lot of work examples in this brochure that feature the indexing head. Here we have the slotting head working on a clutch piece with the indexing head. Over here with the precision boring head on the riser block, doing some pitch hole work. Also on the indexing head with the large faceplate. Here's the rotary table. And here is the page for the indexing. As you can see, there is the old style of the sliding chuck. This allows to move the center of rotation of your workpiece always on center with the spindle of the indexing head. I have the newer version with the 2 axes. It's like a small XY slide that sits on top of the spindle. I've shown that in an older video. This is useful if you want to do work with multiple radii that you have to mill using the rotary table, but you don't want to reset up. You just shift the part around. Oh yeah, there's a rotary table, 55 kilograms. So rigid table, 40 kilograms plus the 55. That's close to 100 kilograms. There's the accessories. There is an example of punch milling with. This is basically the contour or the shape of a small sheet metal part that would get punched out of a large sheet or a strip of material. And with the setup, they are able to cut fairly complex contours on a manual milling machine. You wouldn't do this today. Today, this is wire EDM. You cut this entire profile and it's all good. But back in the day, we didn't have that, so this was an option. There was also the option of using a shaper or a slotter that could do these contours, and a lot of profile grinding. This is a very, very old brochure. I do not know from when this is, but this is the old style of machine. It doesn't have any way guards, no bellows. The speed is set with 2 levers and probably with gears down there. But the overall layout of the machine is exactly the same as it is today. Well, not today anymore. Let's see. I want to show you the punch milling. Well, or a few setups with the indexing head. So that's a fairly complicated part, and they did multiple steps here with the indexing head, always supported up here with the tailstock, using boring head, milling the inside of this housing, using a slitting saw to cut this recess here, and milling the outer contour now on the faceplate. So quite neat. Or over here, machining a fairly complicated aluminium pipe Y or flange adapters thing. Doing complicated internal slotting work here too. These slots are tapered, so they had to do this in two passes with the slotting head tilted to either side, making a reamer, well, a blank for a reamer, with the indexing head tilted very lightly to create the minor skewed cutting edges on this reamer. There is some. This is a mold piece, I think. Yeah, a mold insert machined on the indexing head. So the blank looks like it has been roughly sawn out and then mounted to the sliding chuck. And they're using the horizontal spindle with a large shell mill to rough the contour in. The indexing head can take quite a beating if you consider the size of this cutter. Then they changed over to a vertical head, and they cut the large radii here by rotating the part around, as you would expect with a 26 millimeter end mill. They cut the internal radii with a boring head. And then they switched back to the horizontal spindle to cut this deep slot with a single flute cutter. I mean, there are many, many steps. I don't have to show you all of them, but I wanted to mention a few of them. Still with the horizontal spindle, using a Woodruff key cutter to cut basically a T-slot, but along the Z-axis. And down here, they're using a D-bit single flute cutter to cut the radius on those vertical ribs. They are like radiused, and they do multiple facet cuts by spinning the indexing head a little bit, cutting a facet, spinning it, cutting it, and later the remaining facets are blended by the mold maker by hand. That's a very common work approach back then. Here is the punch milling concept explained. They go into great detail here, showing what you would work off. This would be the drawing that the machinist or the tool maker gets and what he has to work off. All the radii, the center point of the radii are dimensioned of a common point. That's what he uses as a guide. Up here is a demonstration how the radius cutting is done with the horizontal spindle and doing the incremental cuts. So you would cut a facet, rotate it a little bit, and so on, and do that multiple times. Same for internal radii, if you couldn't do it with the boring head, for example. This entire concept required some in-process measuring tools. They had calipers that would fit the overarm support. So you could measure, down here you can see, you could measure the radius that you just machined with the rotary table with this caliper. But you also have over here, this is not a magnifier, this is just a glass with graduation etched onto it. And then you have a small magnifier to look through. So you could measure and gauge radii and internal and external radii that way. And this is also on the center line to the spindle of the indexer. This entire system was quite intriguing, and as you can see by the work examples here, they did some fairly complex parts with this technique. Often they would make a small template out of thin brass and solder it onto the blank as a template to work after for roughing out. You can see it a little bit in this picture that there is like a bright line on the top of the part all the way around, and that's the brass template that's soldered on there. You would unsolder it later, of course. Down here, just some more examples, and by looking at this dimension here, 34 millimeters across, there are some fairly small details, but it gets better. They show this tiny punch, round shank. This is a punch for making zipper parts, for like on clothes. 3 millimeter across here. This is really small, but 18 millimeters long. You wouldn't be able to mill this back in the day. You wouldn't be able to mill this standing vertical and walk around with a small end mill. They were not far enough in cutting tool technology at the time. Small microcarbide cutters were not the norm yet. There is another neat part, and this piece here has this little nose sticking out the side, and that's on the punch here, and this is undercut on the punch, and here is the matching D-bit that they made for it. Well, 2 D-bits even. If you had the D-bit grinder in this machine and all the stuff, you could make some fairly complex parts. I think in this picture, this is, they are cutting the outside radius here, this curved surface. And if you look very carefully, you can see the facets a little bit when they spun it around, took a cut, spun it around, took a cut, and so on and so on. That also allows to have a sharp corner here. If you would cut this from above, walking with an end mill around, you will always leave the cutter radius in this corner. And sometimes that's not desirable. And I kind of like this picture. You have the Deckel school, for lack of a better term, where customers that purchased the machine could also book a course to learn the machine. You have a guy working on a FP1 here. This is a GK, probably a GK12 die sinker. Back there is a Deckel FP1 again. There's a row of engraving machines. And yeah, you would learn your machine there. What I really want to show you is that the indexing head was really a major part of this machine system. Despite not having all the parts in, mostly the washers, I decided to take the rotary table and the rigid table off the milling machine and put the indexing head back on here, because all the indexing head parts sitting around at every flat spot in the shop is driving me mildly insane. And I can change out the washers later. That's not a problem. So let's get this rotary table off here. Doesn't hurt to put on a little bit of something like LPS3 or microcrystalline wax to the mounting surface. Just to prevent any weird corrosion issues. I don't run water-based coolants, as I mentioned. But still, I use, when I machine aluminum, I use alcohol, and that can lead to rust. So a little bit of something that will dry does not hurt. Okay, this goes on here. That doesn't feel like there's anything wrong. Boink. The indexing head is keyed against the apron, and since it's pulling down on the keys, this is very accurate compared to something like keying a vise to a mill table. There you have to push it up against one side of the T-slot to get it really, really accurate. But here, gravity is helping us. Just tightening it in place so it doesn't slide around on me. Again, mounting surface. First going to stone it, and then I'm going to, because there is, it's just dirt. I'm going to stone it, and then I'm adding a little bit of LPS3 to it. I'm going to put the LPS3 also in the T-slot and on the T-slot screws, just to prevent any long-term problems. Okay, let's finagle this in place again. This goes here. Yeah, this part it's not super lightweight. Let's get some washers and nuts on here. Well, I mean, I could. I lost one of the springs of the clamps that holds the overarm support. I'm winding a new one from pre-hardened spring steel wire. Spring winding on a lathe is quite fun thing to do if you're interested. This old Tony made a quite good video on it. And, well, maybe I will do one in the future too. So this is just pre-hardened spring steel from a steel supplier, turned on arbor with cross hole, and I reduced the diameter of the arbor until the spring that I wanted came out with the desired spring back. because you wind it tight and then you cut the wire and then it goes sproing. Then it ends up slightly larger. I made 2 new springs, just cut them off with bolt cutters and cleaned off the end on the bench grinder. And these springs are there to tilt these locks out of the way when the locking screw is undone. Not sure how to assemble this, to be honest. I think you are supposed to squeeze them in like this. Okay. Let's see if this works. Yeah, the lock closes up when you tighten the screw, and when you loosen the screw, the lock releases itself, so there is never a situation where it will bind up. So kind of embarrassing that I lost one of the springs, but I'm going to let myself stop by a lost spring. And the cover goes back in since I don't have to use the overarm support most of the time. This overarm support is really nice. It looks like a piece of, like it's machined from a piece of wooden burl, but it is a phenolic, a resin part that has been machined. So locks work perfectly fine. Very happy that the indexing head is finally back together. This took a little bit longer than I expected, but I had to squeeze the time working on the indexing head between my regular customer work, which didn't require the milling machine, fortunately. Otherwise, this would have been priority 0.5 compared to priority 7. But it's back together, it's fully operational. The warm drive works very, very nicely. And I can put my 0-point plate back on here. Work holding on this thing is quite interesting. You have the 40 taper on the inside, so it takes everything that goes into the mill spindle also in here, no matter if it's collet chuck, if it's a drill chuck, the hydraulic chuck that I use, collets, all sorts of collets go in here. And for larger work holding, you have the outer diameter with 4 conical holes here. And all the work holding that goes on the outside of the spindle, like this large faceplate here, all these things have 4 decent sized set screws that engage in the tapered holes in the sides of the spindle. And the holes in here are offset by a little bit, so the screws not only push on the outer diameter, but also they pull the face of the spore against the face of the indexer. So it's almost a dual contact. It's the 4 screws radially, and it's a face contact. And this makes this work holding, or this interface for work holding, relatively good for how primitive it is. Personally, I would prefer it to be a standard lathe spindle. Like, would be really cool if the spindle was the same nose as my lathe, means a short taper 4 with bayonet disc. That would be super cool because you could swap back and forth very easily. But I have the Lang 0-point system on here. It's this monstrosity here, which allows to quick change work holding between my milling machine and my CNC mill. And the 0-point plate has basically a ring mounted to the back of it with the 4 set screws. And this pulls the face of the indexer directly against the back side of the Lang 0-point plate. I think it's a little bit less stiff in overall, but for what I do, it's most of the time fine. I never found this interface to be a problem. This just slides on here like so. This is a would be nice if it went on straight. And then you tighten these 4 screws on the circumference. And make sure you align the set screws with the hole of with the holes in the spindle. Doesn't hurt to tighten them over diagonals like you would a car tire or any flange connection. I'm even going so far to use a torque wrench on these. So I'm semi-tightening all of them, just so everything settles. And then I tighten it to 15 Newton meters. There we go. And now I can drop anything that I have with the 4 lang bolts, like the small self-centering vise back on here. Just by tightening these 2 screws, again with torque wrench, I'm ready to go. So the indexing head is back together and fully operational again. Thanks for sticking around that long with me. To be honest, this has been one of those videos that was really painful to make. Not only problems with the indexing head itself breaking, but also kind of technical troubles while filming. I promise I will one day figure out audio in videos. I promise it. It won't be tomorrow and it won't be next year, but I will figure it out eventually. But until then, thank you for the support. Thanks for sticking around with me that long. When I look in the comments, I see people who comment for like the last 10 years, which is quite amazing. And thank you all for that. So see you next time. I'll be back.